Well, so today we shall learn how to calculate deflection of RC beams, reinforced concrete beams. If we take the formula for calculation of deflection is very easy. If we take say simply supported beam, if we take a simply supported beam of say span L, uniformly distributed load W, the deflection, the central deflection say delta max, that is equal to 5 by 384 W L to the power 4 by EI. We do not have any confusion regarding W, the uniformly distributed load over the span L, but we are having problem that E and I, because for reinforced concrete, when you are talking say reinforced concrete, we have to calculate that E and I. So far we have designed for the cracked section. That means the only compression part that is uncracked, but bottom wherever we have reinforcement, that crack may appear. So what is the value of E and what is the value of I? That is the major difficulty here. So far the formula concerned, formula looks very simple, but providing that proper value of E and I will give result that one differs significantly if we could not provide E and I. So we shall find out. So what is the problem? Let us find out. So what are the difficulties? Difficulties in calculation. Number 1, let me write down, variation in flexural stiffness, that means EI, along the span owing to what for? Owing to the uncertain nature and extent of cracking. So we face difficulties because variation in flexural stiffness E and I, that EI, that is the flexural stiffness along the span, along this span, owing to the uncertain nature and extent of cracking, because we do not know the cracking also not uniform, and also that uncertain, that wherever the crack will, there is no uniformity. So this is one of the cases. Number 2, variation in sinkage and creep. These are the two properties we have told in the very beginning of our class. Owing to what for it happens? Number 1, it may happen for curing, that how you have cured. Then humidity, exposure, composition of concrete, and also age at loading, that when you are loading this structure, it depends on that also. So, these are the difficulties we may face due to these two cases, that flexural stiffness, because we do not know the proper EI, it is not uniform like steel, and number 2, due to shrinkage and creep, and it may happen due to say curing condition, that means after the casting how it is cured, humidity, exposure condition, whether mild or that different exposure conditions, and then composition of concrete, what grade of concrete you are using, that is it also matters, and also age at loading, when you are loading that, what is the age of the concrete, depending on that. So, this form we shall use the same formula, only we have to provide that proper E and I. We also write down the same formula, say delta, let us write down it as 5 by 384, then W L to the power 4 EI, and we can make it as a say F by EI. F means here in this case, what is F? F equal to, we can write down 5 by 384 W L to the power 4, and it is this one, it means we can say due to load span arrangement. So, this value we are getting it here, that F equal to 5 by, that is for if it is uniformly distributed load over a simply supported beam, then we shall get this factor. So, EI is that value. So, F we are getting, that is almost say we can say determinate. The other part only we are facing difficulty. So, we can write down one more example we can show. Let us say uniformly loaded by moment, bending moment, that is uniform over the whole section. So, if we take a beam uniformly distributed load, a simply supported beam, and moment is M, that is uniform bending moment. So, we can find out delta max. Delta max will be equal to, for this case the central deflection delta max, that one we shall get it as M L square by 8 EI. This is the one, the deflection we shall get it. We can find out also here that for this form, I do not know whether you know the moment area theorem. So, according to that also we can find out deflection, otherwise you can do it other way also, but anyway. So, delta max equal to M L square by 8 I. So, we can write down it as 1 by 8 times M by EI times L square, which comes as 0.125 M by EI times L square. In other way, we write down this equation as beta times psi times L square. Beta means this coefficient, equal to 0.125, and psi, that is your that curvature, because psi equal to M by EI, or 1 by rho, that one we can say, and L is the span. So, we can write down in this fashion also, that formula we can write down. in fact, what we do actually, this value we use it for say shrinkage. Indirectly we shall supply this value beta, psi, all those values we shall supply, and on the basis of that we can find out that what is the deflection due to shrinkage. Okay. So, before going to that, let me give you the reference, that is your Annex C. Annex C, that is calculation of deflection, and it is in page 88, IS 456 2000. There is one term is called, that is your say C2, clause C2, that is your short term deflection. Short term deflection. And let me give you the formula, that whatever given, that I effective equal to IR. Please note there are so many unknown things we are writing. IR minus MR by M times Z by D times 1 minus X by D times BW by B. So, IR, at least let me write down few things. IR, that is second moment of area of the cracked section IR, this is IR, that is the one second moment area of the cracked section. MR, that is cracking moment, MR, that is cracking moment, and which will be equal to FCR times IGR, one more term, divided by YT. FCR, modulus of rupture, and that we shall take it at 0.7 root over FCK. FCK again you know that is characteristic strength, 0.7 root FCK. 0.7 root FCK we shall get it in a clause, that reference I think I should give, of IS 456, that is clause 6.2.2. You will get it as flexural strength, also modulus of rupture, of page 16 IS 456 2000. So, FCR you will get it, this formula you may refer it to clause 6.2.2. Okay. Then FCR we know. What about IGR? So, our main difficulty here to find out this I effective. IR we have to find out, that we shall show you with an example. MR, that is the cracking moment. So, from there FCR we can directly get. So, if it is M20 grade of concrete, so I can get it FCR directly. What about IGR? IGR, that is gross second moment of area. That means overall section, we are not taking any say cracked section or anything, that overall section whatever we shall take it, that is the one IGR. And YT, distance from centroidal axis. Of gross section, and here we shall take it in the tensile one. Say if we take a section, if this is your section, so YT will be, we are assuming that tensile one in the bottom, so this one we shall take it as YT, and BW, obviously BW, this is BW, and this one we shall take it as B or BF, whatever we call it, B. So BW is the width of the web, and then B, that one is a flange, and D, and overall depth, that is a capital D. So for gross section we shall take it overall depth D. X, I think that one, that is neutral axis. So from the top we can take it the neutral axis depth, and Z lever arm. And what about M? One more term is there, M, maximum moment under service loads. Okay. So if we now come back to the formula again once more, I hope I have defined everything. So let us find out whether anything left or not. So this is our formula, we have to find out I effective, and here also there is no end to it. So I effective equal to IR, IR we have to find out for the cracked section, MR cracking moment we shall find out from here, where IGR is the for the gross section, second IT also we can calculate for the gross section, Z lever arm, D effective depth, X the neutral axis depth, BW width of the web, and B width of the flange. So everything we know, so we have to find out. And here it does not end here, there is one restriction, and that I should say that IR, it should be that I effective and IGR. That means whatever we are getting that I effective, that whatever you are getting, if it comes less than IR, then you have to take it IR, that value you have to take it. So I think we can take one example that will be easier. Let us take one T section, and let us assume that we have designed it due to say your applied load. Now we have to check the deflection. So this is 2200. Let us say the slab depth, which is the depth of the flange also 125. Let us say we have got 325 bars, and this depth, that is say 575, overall depth say 700. Concrete M20, we are talking say service load, steel Fe415, dead load, span 7.5 meter, simply supported. Then D equal to, okay, dead load 15 kilonewton per meter. This is the service load, not the factored one. When we are talking to deflection, that one we are talking is a service load. Live load 10 kilonewton per meter. D equal to 700, overall depth 700, minus cover minus 25 by 2, it comes as 662.5 millimeter. Area of steel that is 3 into pi by 4 to 25 square. So, 3 into 491 1473 square millimeter. M, that is the moment, we are getting it here. So, WD plus WL, that is the maximum moment for the simply supported case, WL square by 8, which comes as equals 175.78 kilonewton meter. So, that m r by m. So, this m, that is the maximum moment under the service load, that we have got one component so far. Okay. So, let us find out. So, m we have got it 175.78 kilonewton meter. Now, let us find out that EC. EC equal to 5000 root FCK. In the new code in IS 456 2000 it is 5000. In the earlier code of 1978 it was 5700. Okay. So, okay. So, moment you have got 175.78 kilonewton meter, and area of steel you are getting 1473 square millimeter. Effective depth 662.5 with clear cover 25 millimeter, and that bar we have used say 25 dia. So, which we have got it. This one you can say that you have got this information everything from your say either by working stress method or by limit state method, that you have got these values. Now, you are checking the deflection, and which you will do it by say under working stress condition, that means under service load. So, EC we are getting here say 5000 root FCK, and which comes as 22361 Newton per square millimeter. Modulus ratio, that modular ratio, there is one more formula, but we can use directly this formula also, ES by EC. For steel it is this Newton per square millimeter, and which we have got it for concrete. From the flexural strength we are getting that from the characteristic strength we can find out EC, and which comes at 8.94. So, modular ratio M, that we have got it 8.94. Now, what about FCR? FCR equal to 0.7 root FCK, already I have told you, that is in clause 6.2.2 page 16. This value also you will get it in the same page 16, the next clause of IS 456, and which comes as 3.13 Newton per square millimeter. You will get it as a flexural strength, also modulus of rupture, which is defined in the list of symbols in IS 456. Let us assume X is less than 125 millimeter. I mean to say that your neutral axis will be within your flange, then our problem will be easier. So, this is your 125, that is the slab also we can say, or depth of the flange. So, neutral axis may be somewhere here. So, this is your X. So, if that be the case, so we can use the transformed section it means half, this is your B times x square, that means B times x into x by 2. B times x is the area times x by 2, that is the one we are taking with respect to neutral axis. That one should be equal to modulus ratio times AST. this one will change the transformed section, this one will change the steel to the equivalent concrete section times d minus x. So, I am getting this one, that means with respect to this neutral axis I am taking the moment, and from there we can get these values. So, in our case it will be half, B is 2200, that is what we have given that in the problem. Please I would like to refer it back. So, this is 2200. So, B and X I do not know so far, also you have got it. So, 1473. What about depth? Depth is 662.5 minus x. So, from this equation I can find out that value x. So, from this equation I can get that value x. So, let us just simply write down the equation x square plus 1.05 equal to 0, and x comes as 83.27 millimeter less than 125 millimeter. The assumption whatever we have done it, that is correct, that means it is coming within flange. Now, we can calculate the lever arm. Lever arm working stress method. So, 662.5 minus 83.27 by 3, and it comes as 634.75 millimeter. What about that IR? IR is the for the cracked section, second moment of area of cracked section. That one will be equal to, let me write down the formula first, B times x square by 3. Let me draw a figure. So, this is your B, somewhere here we are having x. So, B, that means we are taking about this neutral axis. So, B x square by 3, we are talking this portion, because this is uncracked one, okay, plus m times AST, where it is AST here, times d minus x whole square. That means, this one your d. So, d minus x. So, this is your d minus x. So, this is your that formula. So, I can write down it 2200 into 83.27 whole cube by 3 plus m is 8.94, which we have computed, times 1473 the area of steel, times 662.5 that effective depth, minus neutral axis depth 83.27 whole square, and which comes as 4.8414 into 10 to the power 9 millimeter to the power 4. So, this is your IR. For the cracked section we are getting for this value. Okay. Now, the other part, distance of centroid from tension fiber. Okay. So, this is your 2200, this one your 125, this is 575 overall depth, this is overall depth 700, the section which you are using, this is 250, and we are interested to find out YT, maybe somewhere here. and yt will be equal to, because from the tension fiber and we are for the simply supported case it is at the bottom. So, yt will be equal to 250 times 700 times 700 by 2 plus, let me write down here, 2200 minus 250 times 125 times 575 plus 125 by 2. We are taking this portion, this is 1, 250 into 700, as if it is, we are taking a rectangle, this rectangle we are taking. So, 250 into 700 by 2, okay, plus the remaining portion which is 2200 minus 250. So, that means this portion times 125, that is the area remaining portion, times we shall get somewhere here. So, this depth, that is your 575 plus 125 by 2, that is what I have written. So, we have made in two parts, one part is that the rectangular portion, that overall, and another one the remaining portion. So, 2200 minus 250, okay, and we shall get it here and divided by 250 into 700 plus 2200 minus 250 times 125, and which comes as 517 millimeter. Okay. So, we have got yt, and let us find out that Ig are the gross moment, second moment of area. Gross second moment of area we can find out, because I know now that 517 millimeter, this one. So, 250 times 517 whole cube by 3, that means I am talking this portion I am talking. So, with respect to this neutral axis. So, 250 into 517 whole cube by 3 plus, let us take the whole. So, which is 2200 into 700 minus 517 whole cube by 3, I am taking this portion, the whole, minus 2200 minus 250 times this portion, that means I would like to remove this portion, and let me write down that one here as 700 minus 517 minus 125, that whole cube by 3, and which comes as 1.588238 into 10 to the power 10 millimeter to the power 4. So, we can get IGR this value. That means, I am taking the only this portion, the rectangular portion at the bottom of the neutral axis, then I am taking the top portion and minus this portion, these two, that is what I have done it here. Okay. You can do it other way also, there is no such, but we generally do it in this fashion. So, what about your cracking moment? MR, the cracking moment, equal to IGR by YT times FCR, which equals 1.588238 into 10 to the power 10 into FCR, we have got it calculated 3.13 Newton per square meter from 0.7 root FCK. YT is your 517, okay, and everything if we divided by 10 to the power 6, then that one I shall get it in kilonewton meter. So, everything was in Newton millimeters per. So, divided by 10 to the power 6 will give me kilonewton meter, and which comes as 96.15 kilonewton meter. So, this is your cracking moment, we have got it, and we know that M also. So, now we shall calculate. So, now we shall calculate our that I effective. So, I effective, that formula we can write now once more. So, I effective equal to IR, let us reproduce the formula once more, minus MR divided by M Z by D 1 minus X by D times BW by B. Let us find out separately 1.2 minus MR by M Z by D 1 minus X by D BW by B, which comes as 1.2 MR, that just now we have computed 96.15, M we know 175.78, W L square by 8, that one, that maximum moment under the service load. Z we have got it as 634.75 divided by D 662.5, 1 minus X 83.27, that also we have computed, D 662.5 times BW 250 by 2200. So, everything we have got it, and which comes as 1.2 minus 0.052 equal to 1.148. So, this is your, we are getting this formula. So, I effective will be equal to IR by 1.148 equals 0.871 IR. But in our case IR, the formula is like this. So, it will be in between. So, here I effective will be equal to IR only, we shall take the correct one only. In our case we shall take I effective equal to IR, because we have to, it should be greater than IR and less than I gross. So, in our case it is coming less, so we have to take it I effective equal to IR. So, now we can calculate different cases. Number 1, deflection due to dead load, that is the permanent load, deflection due to permanent load, the dead load here. So, delta DL we can write down as 5 by 384 into that 15 kilonewton meter, that means 50 Newton per millimeter also we can write down, times 8, it will be 7500 whole cube by E 22361 times that IR or I effective, that is equal to 4.8414 into 10 to the power 9, that is what we have computed. So, we can find out this formula, using this we can find out, and which comes as 5 into 15 3 divided by 3 8, okay, it will be 4, sorry, it will be 4. So, 5 into 15 into 7500 4 divided by 384 divided by 22361 divided by 4.8414, which comes as 5.7 millimeter. It comes as 5.7 millimeter. This is your that 5 by 384 W L to the power 4 by L is 7500, 7.5 meter, 15 kilonewton per meter is nothing but 15 Newton per millimeter, E 22361, which you are getting from 5000 root FCK, and this is yours at I effective. So, we can get 5.7 millimeter. And what about delta LL? The same way we can find out 5 by 384, or we can take the ratio also, 10 Newton per millimeter, 7500 whole to the power 4 divided by 22361 into 4.8414 into 10 to the power 9, and which will be here equal to so 3.8 say. Okay. So, this is your that we are getting the deflection. So, permanent due to the permanent load, and you say service load, that live load. And now we have two more things. One is that one, this is, that means here there is no difficulty, we can find out that EC 5000 root over FCK, and I effective also we can get it from the formula, the one which is given in annex, that annex C, and from there we can find out. Now, the next part is coming, that is your say due to shrinkage and due to creep. So, what we shall do it here, that we do it, that is in clause C3, this is deflection due to shrinkage. What we shall do it here, say delta CS, let us say that one equal to, it writes K3 psi CS L square, that is the formula which is given in clause C 3.1 page 88 IS 456. You remember that I have told you that formula, that beta psi L square. So, for simply supported case, here also it says for simply supported case K3. So, K3 has different values. So, 0.5 for cantilevers, 0.125 for simply supported, 0.086 for members continuous at one end, and 0.063 for fully continuous members. In our case, K3 will be equal to 0.125. Psi CS will be equal to, that is called shrinkage curvature, and that is equal to K4 epsilon CS by D. So, here what happened, actually you are assuming that there is a beam and there is a, due to shrinkage there is a deflection, and that deflection we have to find out, this deflection we have to find out. So, what we are doing, that means indirectly what we are doing, actually basically we are calculating the what is the strain for shrinkage strain, and from there we can find out. So, what about the value of K4? K4, let me write down here that K4 separately. So, K4 equal to 0.72 PT minus PC, that percentage steel, root over PT, that percentage steel tensile 1, this is compression steel percentage, square root of the tensile steel, and less than equal to 1.0 for 0.25 PT minus PC less than 1.0. If this is the case, that means we shall use this formula if we find PT minus PC, difference of the tensile steel and compression steel percentage, if it comes within this range, then we shall use this formula. Otherwise, we shall use the separate formula, that means the change value here, and again it should be less than equal to 1.0 for PT minus PC greater than equal to 1.0. So, let us find out, we do not have any compression steel, we have only given tensile one. So, PT equal to how much, let us find out. PT equal to, so let us find out PT. What about the area of steel? Okay, area of steel here, area of steel 1473 times 100 divided by BW, we shall use it 250, we shall use BW times D 662.5. Okay. So, let me write down here, PT will be equal to 100 AST by BWD and equals 0.889, it comes in this range. So, K4 equal to 0.72, then 0.889 minus 0, there is no PC, 0.889, which comes as 0.6788. So, K4 we shall get it as 0.6788. Okay. So, PT that means, so from this PT we can get K4 0.6788. Now, what about epsilon shrinkage strain? Unless otherwise specified, we shall take shrinkage strain as 0.0003. We shall take shrinkage strain as 0.0003, we shall take it if it is not specified. And so, we can find out that psi CS will be equal to K4 epsilon CS by D and will be equal to 0.6788 divided by 0.0003 divided by 700, and let us write down this one. So, 0.6788 into 0.0003 divided by 700, which comes as 2.9091429 into 10 to the power minus 7, and then delta CS, that deflection due to shrinkage, K3 times psi CS times L square, which equals to K3 for simply supported case, K3 0.125. So, 0.125 times 2.9091429 into 10 to the power minus 7 times 7500 whole square. So, we can get it which comes as 2.04 millimeter. So, due to shrinkage we shall get 2.04 millimeter. And next one we have, that is your creep, and that you will get it in C4 deflection due to creep, deflection due to creep. Okay. And that is in page 89 IS 456 2000. Okay, let me little bit faster. ECC, that is given here, ECC equal to, that is your for the creep, equal to EC by 1 plus theta, and theta that is creep coefficient. There is no such direct method, we are doing it indirect way, and that one we are getting it from your say that experimental values. On the basis of that we get it. So, coefficient, creep coefficient, and generally we take theta equal to 1.5. Generally we take it theta equal to 1.5. So, we can find out say delta C, that is say permanent, equal to the same formula we are using the same way, ECC I effective minus F by EC, this is due to load, that short term load, I effective, and ECC equal to EC by 1 plus theta. So, we can write down this one as F by I effective times 1 plus theta by EC minus 1 by EC, because I am just simply writing this ECC here, and which comes as F by EC I effective times 1 plus theta minus 1, this one, equals F by EC I effective times theta. That means only due to creep, we can get this value. This one actually we can get it only due to creep, we can get the value as, this is due to short term load, this is due to short term load times the theta, theta is 1.5, it is not mentioned, nothing mentioned, so we have to take. So, F by EC times I effective times theta. So, what we can do it then, we can find out, let us go back to the whatever the results we have got it. Okay. So, delta DL due to dead load 5.7 millimeter, delta live load 3.8 millimeter, delta shrinkage 2.04 millimeter, and delta creep, that one we shall get it as that delta DL times theta. That means here it will be 5.7, this is due to permanent load, 5.7 times 1.5, and which will be equal to 8.55 millimeter. So, we can get it here the total deflection, that means this is due to load, short term load, permanent load, this is due to live load that we have got it, this is due to shrinkage we have got it, and we have checked, we have got it that one, this is due to permanent load, dead load times theta will give me due to creep. So, we shall get it 8.55. So, total deflection, so we can get it as say 5.7 plus 3.8 plus 2.04 plus 8.55 equals 5.7 plus 3.8 plus 2.04 plus 8.55, which comes as 20.09 millimeter, almost equal to 20, that means 20 millimeter is the maximum deflection that we can allow. So, it is coming almost this one. Okay. So, this is your that whole calculation regarding the deflection, the procedure that whatever I have given, that one according to IS 456. Okay. So, thank you.